Good morning, everyone. Welcome back to Chemistry 101. Today, we're diving into Chapter 1, Matter and Change. This chapter will help you understand the properties of matter, the structure of atoms, and the organization of the periodic table. Let's get started. Matter and its properties. Definition of matter. Matter is anything that has mass and occupies space. Everything around us, including solids, liquids, and gases, is made up of matter. Matter is composed of atoms and molecules, which determine its physical and chemical properties. Physical properties. Physical properties are characteristics that can be observed or measured without changing the substance's identity. These properties help us identify and classify matter. Key physical properties include color, the visual perception of the wavelength of light reflected by the substance. Odor, the smell produced by the substance. Density, the mass per unit volume of a substance. It is calculated as density equals mass divided by volume. Melting point, the temperature at which a solid turns into a liquid. Boiling point, the temperature at which a liquid turns into a gas. Hardness, the resistance of a material to deformation or scratching. Chemical properties. Chemical properties describe a substance's ability to undergo changes that transform it into different substances. These properties are crucial for understanding how substances interact and react with each other. Key chemical properties include flammability, the ability of a substance to burn in the presence of oxygen. Reactivity with acids, how a substance reacts when exposed to acids. Oxidation states, the degree of oxidation of an atom within a compound. Corrosion resistance, the ability to withstand degradation due to chemical reactions with the environment. States of matter. Matter exists in three main states, each with distinct characteristics. Solids have a definite shape and volume. The particles are tightly packed in a fixed arrangement and only vibrate in place. Examples include ice, metals, and rocks. Liquids have a definite volume but take the shape of their container. The particles are close together but can move past each other, allowing liquids to flow. Examples include water, oil, and alcohol. Gases have neither a definite shape nor volume. The particles are far apart and move freely, filling any container they occupy. Examples include oxygen, nitrogen, and carbon dioxide. Atoms, elements, and isotopes. Atoms. Atoms are the basic units of matter and the defining structure of elements. Each atom consists of a nucleus made of protons and neutrons, surrounded by electrons and defined energy levels or orbitals. Protons, positively charged particles located in the nucleus. The number of protons, atomic number, defines the element. Neutrons, neutral particles in the nucleus. The number of neutrons can vary within atoms of the same element, resulting in different isotopes. Electrons, negatively charged particles that orbit the nucleus. Electrons occupy different energy levels, and their arrangement determines the chemical properties of the atom. Elements. Elements are pure substances consisting of only one type of atom. Each element is defined by its atomic number, which is the number of protons in its nucleus. The periodic table organizes elements by increasing atomic number and groups elements with similar properties together. Isotopes. Isotopes are variants of a particular chemical element that have the same number of protons but different numbers of neutrons. This means isotopes of an element have different mass numbers. Example, carbon has 3 naturally occurring isotopes, carbon-12, 6 protons, 6 neutrons, carbon-13, 6 protons, 7 neutrons, and carbon-14, 6 protons, 8 neutrons. While carbon-12 and carbon-13 are stable, carbon-14 is radioactive and used in radiocarbon dating. Ions, positive, negative, and polyatomic. Ions. Ions are atoms or molecules that have gained or lost one or more electrons, resulting in a net charge. Ions form when atoms gain or lose electrons to achieve a more stable electron configuration. Cations, positively charged ions formed by the loss of one or more electrons. Example, sodium, Na, loses one electron to form Na+1. Anions, negatively charged ions formed by the gain of one or more electrons. Example, chlorine, Cl, gains one electron to form Cl-1. Polyatomic ions. Polyatomic ions are ions composed of two or more atoms covalently bonded that act as a single charged entity. These ions play crucial roles in various chemical reactions and are commonly found in many compounds. Example, sulfate ion, SO4-2, consists of one sulfur atom covalently bonded to four oxygen atoms, carrying a total charge of -2. Nitrate ion, NO3-1, consists of one nitrogen atom covalently bonded to three oxygen atoms, carrying a total charge of -1. The periodic table of elements. Organization of the periodic table. The periodic table is a systematic arrangement of elements, organized by increasing atomic number. Elements are placed in rows, periods, and columns, groups, based on their atomic structure and properties. The table highlights periodic trends that help predict the behavior of elements in chemical reactions. Groups, vertical columns on the periodic table. Elements in the same group have the same number of valence electrons and exhibit similar chemical properties. Example, Group 1, alkali metals, includes lithium, Li, sodium, Na, and potassium, K. These elements have one valence electron and are highly reactive. Periods, horizontal rows on the periodic table. Properties change progressively across a period as the number of protons and electrons increases. Example, period 2 includes lithium, Li, beryllium, Be, boron, B, carbon, C, nitrogen, N, oxygen, O, fluorine, F, and neon, Ne. Periodic trends. Understanding periodic trends is essential for predicting the properties and behaviors of elements. Key trends include: atomic radius generally decreases across a period from left to right due to increasing nuclear charge, pulling electrons closer to the nucleus. Atomic radius increases down a group as additional electron shells are added. Ionization energy, the energy required to remove an electron from an atom. Ionization energy increases across a period due to increasing nuclear charge and decreases down a group as electron shielding effects increase. Electronegativity, the ability of an atom to attract electrons in a chemical bond. Electronegativity increases across a period and decreases down a group. Fluorine, F, is the most electronegative element. Modern-day applications. Understanding the properties of matter, atomic structure, and the organization of the periodic table is crucial in many fields. In medicine, isotopes are used for diagnostic imaging and cancer treatment. For example, technetium-99m is widely used in medical imaging due to its ideal half-life and gamma-ray emission. In materials science, the properties of elements and their compounds are essential for developing new materials. For instance, the discovery of graphene, a single layer of carbon atoms, has led to advancements in electronics and materials engineering. In environmental science, knowledge of ions and their reactions helps in water purification and pollution control. The use of activated carbon filters to remove contaminants from water is based on the principles of adsorption and ion exchange. In conclusion, today, we covered the fundamental concepts of matter and change, including the properties of matter, atomic structure, ions, and the periodic table. Understanding these basics will help you grasp more complex topics in chemistry and apply this knowledge in scientific and practical contexts. These principles form the foundation for your journey in chemistry, preparing you for future topics like chemical reactions, bonding, and molecular structures. Thank you for joining today's lesson on Chapter 1, Matter and Change. Stay tuned for our next chapter, where we will explore molecules and compounds. Don't forget to like, subscribe, and share this video. Until next time. Dr. Siegfried Howell.